is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this video, we are going to determine the differential equation that governs the variation of the current during its growth in an RL series circuit fed by square wave voltage, give the expression of the current during its growth, verify the solution of the differential equation, determine the unit of the time constant tau of the RL circuit, give the value of the current at the instants 0, tau, and 5 tau. Draw the tangent to the curve I equal f of t at t0 equals 0. Finally, determine the differential equation that governs the variation of the voltage UR across the resistor of the circuit.
Differential equation that governs the growth of the current. Consider an RL series circuit fed by a square wave voltage. The voltage across the generator is given by UAC is equal to E during the first half of each period and is equal to 0 during the second half of each period. Now we have to write the differential equation in I. To write this differential equation, it's better to start with the voltage across the generator and then we follow the positive sense so that UAC is equal UAB plus UBC. During the growth of the current, UAC is equal to E. So UAC can be replaced by E. Since the positive sense is oriented from A to B through the coil, so UAB is equal to Ri plus LdI by dt, where the small r is the internal resistance of the coil and L is the inductance of the coil. Similarly, the positive sense is oriented from B to C through the resistor, so UBC can be written as capital R times I. Rearrange by taking I as a common factor, so R plus R into I plus LdI by dt is equal to E. Now divide by L both sides, so di by dt plus R over L times I is equal to E over L, which is the first order differential equation that governs the variation of the current during its growth.
So this is the differential equation that governs the variation of the current during the growth process. The solution of this differential equation is given by this expression, Im into 1 minus e to the power minus t over tau. Im is the maximum value of the current during its growth. Im is equal to E over the total resistance of the circuit. Look at the figure. The total resistance of the circuit is equal to the resistance of the resistor plus the internal resistance of the coil. What is tau? Tau is the time constant of the RL circuit. Tau is equal to L, the inductance, over the resistance of the circuit. Now, Im and tau are constants. Tau is the time constant, it is called so the time constant of the RL series circuit, and it is a characteristic for the RL series circuit. Now, if we replace Im in the solution by E over R plus R and tau by L over R plus R, this is going to be I is equal to E over R plus R into 1 minus e to the power minus R plus R over L into T.
Verification of the solution I equal Im into 1 minus e to the power minus t over tau of the obtained differential equation, where Im equal E over R plus R and tau is equal to L over R plus R. To verify that I is a solution of this differential equation, we have two steps. First step, we differentiate I with respect to time, and the second step, we replace the expression of di by dt and I in the differential equation, and then we arrange the expression to prove that the left side of this differential equation is equal to E over L as that of the right side. Now let's expand the expression of I. So I can be written as Im minus Im e to the power minus t over tau. Before differentiating I with respect to time, let's take this remark. ae to the power bt is a certain expression varies with the time t. A and b are two constants. The derivative of this expression is equal to ab times e to the power bt. Now let's differentiate I with respect to time. Im is constant, so the derivative of Im with respect to time is equal to 0. Now minus Im e to the power minus t over tau is similar to ae to the power bt, where minus Im is equal to a and minus 1 over tau is equal to b. So the derivative of minus Im e to the power minus t over tau can be written as minus Im, which is equal to a, times minus 1 over tau, which is equal to b, times e to the power minus t over tau. This is going to be di by dt is equal to Im over tau e to the power minus t over tau. Now replace di by dt and I in the differential equation. Im over tau e to the power minus t over tau is equal to di by dt, and Im minus Im e to the power minus t over tau is equal to I. So we know that tau is equal to L over R plus R, so R plus R over L is equal to 1 over tau. So replace R over plus R over L by 1 over tau, we get this new equation. Now expand by multiplying Im minus Im e to the power minus t over tau by 1 over tau, we get another equation. As we see, Im over tau exponential minus t over tau minus Im over tau e to the power minus t over tau cancel each other. We get a new equation or a new relation. Im over tau is equal to E over L, but Im is equal E over R plus R and tau is equal to L over R plus R. Now replace Im and tau by their expressions, and R plus R cancels R plus R. So E over L is equal to E over L. Since the left side is equal to the right side, the expression of I is a solution of the differential equation.
Let's determine the unit of the time constant tau. Tau is given by this expression, L over small r plus capital R. So the unit of tau is equal to the unit of L, which is the Henry, over the unit of the resistance, which is the ohm. Now, the magnetic energy stored in a coil is given by this expression, 1/2 Li squared. Rearrange. L is equal to 2W over I squared, which means that the unit of L is equal to the unit of energy, which is the joule, over the square of the unit of the current, which is ampere squared. Again, P is equal to Ri squared. So this is a formula for the power. Rearrange. R is equal to P over I squared. So the unit of the resistance, which is ohm, is equal to the unit of the power, which is watt, over the square of the unit of the current, which is amperes squared. Now, replace the Henry by joule over amperes squared and ohm by watt over amperes squared. This is going to be the unit of tau is equal to joule over amperes squared over watt over amperes squared. This is going to be joule times amperes squared over watt times amperes squared. This is going to be joule over watt. Now also, if you want to calculate the power, then you divide the energy by the time, which means that the watt is equal to joule divided by second. This is going to be joule is equal to watt times second. Now replace watt in this expression by, replace joule in this expression by watt second. This is going to be the unit of tau is equal to watt times second over watt, which is equal to seconds, which means that the SI unit of tau is the second.
Focus, please. This is important.
Now, referring to the expression of the current during its growth, let's determine some particular values of I at specific instance and when t tends to infinity. Let's start when t is equal to 0. So replace t equals 0 in the expression of I. We get I of 0 is equal to Im into 1 minus e to the power 0. But e to the power 0 is equal to 1. Therefore, during its growth, the current starts 0. Now, let's determine the expression of the current at t equal tau. So replace t by tau in the expression of the current. We get I equal Im into 1 minus e to the power minus tau over tau, which is equal to Im into 1 minus e to the power minus 1. But e to the power minus 1 is approximately equal 0.37. Therefore, I is approximately equal 0.63 Im. So we can write at t equal tau, 63% of the whole growth process is completed. Now at t equal 5 tau. Similarly, replace t by 5 tau in the expression of the current I. We get I at t equal 5 tau is equal to Im into 1 minus e to the power minus 5. But e to the power minus 5 is approximately equal 0.007. This is going to be I equal 0.99 Im, which is approximately equal Im. So we can write at t equal 5 tau, 99% of the whole growth process is completed. Practically, the steady state is attained. Remark: the expressions of I in terms of Im at t equal tau and at t equal 5 tau have to be memorized by the students, unless otherwise they are asked to prove these expressions. Finally, let's determine the value or the expression of I when t tends to infinity. We know that e to the power minus infinity tends to 0. Therefore, when t tends to infinity, the current tends to Im. So we can write I1 equal Im is a horizontal asymptote of the current during its growth.
Let's study the tangent to the curve I equal f of t at t0 equals 0 in the growth process. So here in this graph, we have the blue curve. It represents the current, the variation of the current, and we draw the tangent to this curve at t0 equal 0. Now we have the expression of the current in the growth process. Expand the expression. This is going to be Im minus Im times e to the power minus t over tau. Now we want to differentiate this expression with respect to time. Remember, if you have a function y of t which is equal to e to the power u, then the derivative of y with respect to time is equal to u prime times e to the power u. So here, this is u. Now we want to differentiate this expression with respect to time. Let's start with Im. Im is constant, so its derivative with respect to time is 0. Minus Im is a constant multiplied by the exponential, so it stays the same. Now, what is the derivative of e to the power minus t over tau? So what is u prime? U prime is equal to minus 1 over tau, and this is e to the power u. Now this is going to be Im over tau times e to the power minus t over tau. Now we want the derivative at t0 equals 0. So replace t in this expression by 0. This is going to be Im times e to the power 0 over tau, which gives you Im over tau. Now you know that the derivative of a function at t0 equals 0 is equal to the slope of the tangent to this function at t0 equals 0. Let's move to the curve. We want to determine the slope of this tangent on the graph. The slope is given by delta I over delta T. So you can take 2 points. The first point is 0, 0, and the second point is T1 is its abscissa and Im is its ordinate. So the slope becomes Im minus 0 over T1 minus 0, which is equal to Im over T1. Now, by comparison, you will observe that Im over tau is equal to Im over T1, which means that T1 is equal to tau. Now, so this is tau. Now, what is the conclusion of this study? The tangent to the curve I equal f of t at t0 equals 0 meets the horizontal asymptote of equation I1 equal Im, this is the horizontal asymptote, at a point of abscissa tau. Now we can use this conclusion when we want to draw the tangent accurately on the curve.
Differential equation that governs the variation of UR equal UBC. Applying Kirchhoff's voltage law, UAC is equal to UAB plus UBC. During the growth of the current, UAC is equal to E, and we have the positive sense oriented from A to B through the coil, so UAB is equal RI plus LdI by dt, and we have UBC equal UR. We know that UR is equal Ri, and R is constant, so DUR by dt is equal to R times di by dt, then di by dt is equal 1 over R times dur by dt. Now replace I by ur over R and replace di by dt by 1 over R times dur by dt, we get this equation. So take UR as a common factor, then we have a new equation. Multiplying both sides by R over L, we get this equation. Now R cancels R, L cancels L, therefore dur by dt plus ur into R over L plus R over L equal ER over L. Now, by taking L as a common denominator, we write the final differential equation in UR, which is dur by dt plus R over L UR equal ER over L.
Now we want to draw the curve that represents the voltage across the coil UL as a function of time. First, for ohmic resistor or ideal resistor, UR is equal to RI, which means that UR and I are directly proportional. Therefore, the curve of UR is similar to that of I, differing only by a constant multiplying factor, which means that if the current increases in the growth process, then UR also increases with time. Now, in the previous slide, we have E is equal to UL plus UR at any instant. Now, UL is equal to E minus UR. So, UL decreases exponentially with time because E is constant and UR increases with time, which means that UL decreases with time. So this is the graph. We have the curve of E, which is a straight line, horizontal and parallel to the time axis. Because E is constant, UR, as you see, increases with time, and UL, which is equal to E minus UR, decreases with time. Now I have a question for you. UL does not reach zero when the steady state is attained. Can we explain this? Now, the expression of UL is equal to Ri plus LdI by dt. But in the steady state, di by dt is equal to 0 and I is equal to I max. So, replace di by dt by 0 and I by I max in the expression of UL. This is going to be UL is equal to I max, which shows you that in the steady state, UL is not equal to 0 because it has an internal resistance, so it acts as a resistor.
Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button, and share.